Next, I'm going to review the chain rule, product rule, and also quotient rule. So next, we're going to go over the chain rule. The corresponding section for the chain rule is section 3.4. So you probably want to read over your textbook to review that. The chain rule talk about when you have a composite function, okay? So you have this outer function and inner function. When the inner function is differentiable at x, and the outer function is differentiable at g of x, then when you differentiate this composite function, then what happens here is you will take the derivative of this outer function and evaluate at this inner function, and then multiply by the derivative of the inner function. Well, it is like peeling an onion. So when we peel an onion, okay, we'll peel from outside to inside, okay? So the outer layer will get peeled first, and then we get to the inner layer, okay? So we differentiate the outer, and then later on we differentiate the inner. So, and you multiply that, okay? So this, another notation for the chain rule is this notation. It's called
Leibniz.
Leibniz notation, okay? So this is another notation for the chain rule, okay? So it says that if y is a function of u and u is a function of x, okay, then what happens here is when you differentiate y with respect to x, it is the same as you differentiate y with respect to u and then multiply by the derivative of u with respect to x. So now if you're looking at this expression, well, it looks like the du here cancel out, right? Okay, and give you back dy dx. Okay, so this notation is a little bit easier to remember, okay? It also reminds you of the chain, right? So this is the first ring of this chain, and then this is the second ring of the chain. Well, if the function is a composite of multiple functions, then you will have more chain over here, okay? So that's the chain rule, okay? Okay, now let's look at this example. We're trying to differentiate y equal the sine of x squared, okay? So think about this, the outer function, okay, is sine of u. Now think about this x squared here as u, okay? This x squared over here as u. So we're going to differentiate sine of u with respect to u. So we'll get cosine of u. Okay, with the u over here being this x squared. Okay, now the inner function is x squared, and then we differentiate that with respect to x. We're going to end up with 2x. Okay, so the chain rule says that if we differentiate this y with respect to x, then that will be the product of this one and this one. So that will be cosine of x squared times this 2x over here. Now notice that I put a parenthesis over here because if you don't put a parenthesis, sometimes it looks like the x squared is being multiplied with the 2x. So it's better to put a parenthesis if you put them this way. A better way to write this is to put the 2x in front. So we'll have 2x times cosine of x squared. Now let's look at the second example, y equals sine square of x. Notice that this is the square on this side is the same as square this sine x. Okay, so you have sine x here, and then you square this whole quantity. Okay. Now, the outer function. Okay, if you think about this sine x here as u, then the outer function will be u squared. When you differentiate this outer function with respect to u, you have 2u. And now we differentiate this inner function with respect to x, we end up with cosine of x. So by the chain rule, the product of the derivative of y with respect, so by the chain rule, the derivative of y with respect to x is equal to the product of this one and also and this one. Okay, so we end up with 2 sine of x because u equals sine x, and then times this cosine x. Now this, we might use the double angle formula. Sine of 2x is equal to 2 sine x times cosine x. So this is equal to sine of 2x. Now next, we're going to review the product rule. The product rule says that if you have the product of 2 functions, then you're going to differentiate the first function and then times the second, and then adding that with the first function times the derivative of the second function. Looks like they take turn to differentiate. The first time we differentiate this, the second time we differentiate that, right? And here is a plus. So for example, this function, we'll differentiate the x first here, and then in this one, we'll differentiate e to the x. Well, the derivative of x is equal to 1. The derivative of e to the x is e to the x itself. So the result here is this. Now we can take out this common factor, e to the x. So we have e to the x times 1 plus x in the parentheses. Okay. Next one, we're going to review the quotient rule. When you have this quotient of f and g, now the derivative of that is denominator is going to be g squared, and then on top it has a similar pattern as the product rule. So f prime g here and the fg prime over here, but in between it is the difference, so subtracting over here. Okay. Now, for example, this is a quotient. Now the derivative y with respect to x, so the denominator here will have the square of this. And over here, we're going to take turn to differentiate. The first differentiate the function on top here. And then for the second one here, we'll differentiate the function in the denominator over here. Okay. And in between, it is a subtraction. Now remember, the derivative of e to the x is e to the x itself. And the derivative of 1 plus x squared is the derivative of a constant is going to be 0. The derivative x squared is 2x. So this is equal to x. Now combine and take out this common factor e to the x. We combine this over here. And notice that this reminds you of the perfect square formula. This is a perfect square of 1 minus x. Okay? So this is the answer over here. Okay? So this is using the quotient rule. Now let's take a break.